Welcome, this is the third part in the 6th week of the Parallel Programming Concepts course in OpenHPI. After we saw Foster's methodology and several parallel programming design patterns, we now want to talk about the so-called Berkeley Dwarfs as one idea of summarizing interesting parallel problem domains. Our teaching team did an investigation of parallel software recently in order to get a better understanding of how people do parallel programming. So what kind of problems do they want to solve? What is the kind of code you can typically find? So we took our own parallel programming courses from other people, parallel benchmarks, development tutorials for libraries such as IntelTPB, books, and also user stories from the internet. And we tried to do some statistics on what kind of problem is really relevant. What is the kind of underlying algorithmic issue people want to solve with parallel programming. And it turned out after a while that you find reoccurring patterns of algorithmic problems in these different source codes. So you could see that people often deal with structured data problems, with matrix operations, either 2- or 3-dimensional. We had decomposition problems, also a lot of reduction problems. Vectors were very important. So many things repeated in the way that you can say there are algorithmic classes, algorithmic problem classes that are typically tackled by parallel programming. And this is an investigation which was very interesting, but which was by far not new. So what we basically did there was we proved an insight that other people also had beforehand, and this is what is called the so-called Berkeley Dwarfs. So in 2006, the University of Berkeley published a technical report which was called The Landscape of Parallel Computing Research. And this technical report became quite famous because it defines the so-called dwarfs, which is 13 common designs of parallel computation and communication. So the authors here investigated, as in our example, a lot of benchmark suites and example codes. They also took their own decades-long experience in high-performance computing, and they were putting this all into an overall categorization of interesting computational problems for parallelization. Why is this helpful? Why is it good to know how people do parallel codes? The idea is that if you have your own parallelization problem and you can match it to one of these classes, to one of these dwarfs, it becomes way easier to find existing solutions. As I said at the beginning, the most efficient way to do parallel programming is to use the work of somebody else who did all the debugging, who considered all the race conditions and the programming problems. So here the dwarfs are intended to give you a common vocabulary and a common classification of such algorithmic things. Sources, as you see, were a lot of different materials, not necessarily only from high-performance computing, but this was a big part of this report design. And the authors try to make very clear that this is not really intended to be a code example. So there is no source code in this report, but this is more an abstract definition of algorithmic problems, and you can easily map them to one or the other programming language, to OpenCL, to OpenMP, to MPI. The underlying problem remains the same. The authors also hope that these dwarfs can help in doing feasibility studies of hardware and software. So the question of is this parallel programming language useful? Are the new concepts really necessary? Or is this particular parallel hardware something where specific applications can benefit from? And the hope is that based on the dwarfs, this can become much easier in such a discussion. So the current collection of dwarfs looks like this. We see that are things like linear algebra in there, but also grid designs in your algorithm or graphical models. And it can be expected that this list is not finished, but currently it looks like that most of the interesting parallelization problems, at least in scientific computing, are represented here. This led to the fact that in scientific literature and in publications, there was a comparatively large uptake of this idea. So you can meanwhile find a lot of conference papers that relate to the dwarf concept and say our solution is aiming at this or that dwarf. And we meanwhile also see reference implementations of these problems for CPUs, GPUs, and other kind of hardware. This is a short overview of the relevance of different dwarfs in a particular application domain. So red means hot, this means it's very important in this particular domain, and blue means cold, so there is not such a big relevance. And the main message from this picture is that red is spread over the different dwarfs. So different dwarfs, different algorithmic classes are relevant for different application domains. So it's not the fact that one particular dwarf is overly useful and helpful in all application domains for parallelization, but you have a focus on one or the other thing. You can also see that some dwarfs have more potential or are more relevant in many application domains, while some dwarfs are only relevant in one of them. So this relates to the particular problem that is solved in this dwarf. So let's have a look into different examples for these dwarfs. If you want to know all of them, if you want to have the complete overview, then please check our recommended readings. The report is linked there. It's free, available in public, so you can read the original description of all these problems. The first dwarf is called dense linear algebra. And here the idea is that we summarize a problem class where parallel computation acts on vector or matrix data that is non-sparse. Non-sparse means that you have a lot of different elements, not zeros a lot, but a lot of different elements, so it's non-sparse data. And you now do computational operations on this data. So you either want to perform a numerical operation between two vectors, or a vector and a matrix, or two matrices like multiplication. And the nature of the data is non-sparse. So this leads to the fact that you have a lot of data dependencies. So you have a lot of problems with respect to data distribution. You can't really summarize parts of the data or compress them or express them in a different way because it's non-sparse. And therefore you have to deal with that fact in your parallelization strategy. The counterexample to non-sparse data is sparse data, and therefore this dwarf is also called sparse linear algebra. So again, you want to perform the same kind of operations, linear algebra operations, but this time your input data and maybe also your output data is sparse. So as you can see in the picture, you have a lot of empty space in there. And in order to compute bigger problems, as we saw it in Gustafson's law, the typical way to deal with such problems is to have a compressed representation of your input data in memory. So you're not storing all the zeros in main memory, but you use smarter data structures and more clever ideas in order to represent your data. But this leads to the fact that your computation, your attempt to parallelize computation, completely changes, because now you need to work with these dense blocks, these created, summarized blocks of data in a way that you get efficient computation still, although you don't have the original data structure of the problem. And one of the experiences with sparse linear algebra was that scatter-gather vector operations are helpful here. The report also contains some other hints of how to tackle this particular dwarf problem. The next big class of computational problems, and this is clearly from scientific computing, is n-body problems. An n-body problem is one where you have the computational task of calculating relationships between one element and all the others in a particular 2D or 3D environment. So you have interactions between many, many discrete points, and this is an issue because basically global communication is a bad idea from a parallelization point of view. So somehow you need optimized ways of structuring these interactions in data and in computation in order to get a good and feasible parallelization. So you see some examples on the slides and also in the report that tree-based methods and mesh-based methods are helpful here in order to tackle this class of computational problem. The typical concept is that you have a lot of independent computations here, and after a while you have a global summary of a result until you go into the next step. So this is similar to something that is called synchronous processing. The next example for a dwarf is structured grid. Structured grid is the idea that you have a regular organization of your data, and communication between the parallel activities happens in a local way. So computational tasks typically communicate with their neighbors, but not with all other points. And the overall computation, the progress of the algorithm, is a sequence of grid updates. So you have a round-based concept where in each round all the neighbor communication happens, hopefully in parallel, and then the next round starts. If this sounds familiar, this is what we called a heat map example in our coding exercises. But you can also use this for other, for example, physical simulations or in climate simulation and other areas. So the good thing about this is that you have a good structuring, so you can make a lot of use out of this temporal locality, and you really can focus on using caches, using fast memories, fast local memories in order to get real speed up here. You may also want to use a ghost cell approach in order to hide some communication latency. So this is something that is well known and proven in practice, and there are a lot of ideas of how to optimize a structured grid problem for a particular execution environment. The opposite is an unstructured grid. This is also another dwarf where you have still neighbor updates, so you still have communication with neighbors, but the neighbors are no longer in a structured 2 or 3D grid organized, but they have arbitrary positions. And so this makes access management and data distribution a little bit more complicated. It is a very useful approach in simulations, for example, when you talk about physics simulations. But the problem here is that the irregularity of the different tasks in the data room makes it harder to do a right mapping on a particular execution environment. So agglomeration, when we think about Foster's methodology, is still possible and okay, but in the mapping step you start to get a problem and you need to really take care that this works in the right way. The next dwarf in the Berkeley dwarf definition that may sound interesting is the MapReduce dwarf. We already talked about MapReduce, but the more relevant message here is that the MapReduce dwarf was used to be called Monte Carlo dwarf. Both things, so MapReduce is now intended to express a more generalized class of problems where Monte Carlo simulations fall into. A Monte Carlo simulation is one where you take a random number generator and you have a lot of these random number generation rounds. So you do an independent execution of a particular function in order to get data inside of your simulation. And now the question is, how can you parallelize this? When you take MapReduce, then you could now argue that this is also the independent execution of the same function, in this case the map function, on particular different data items. And therefore the idea here is to put them into one dwarf. At the end you have an aggregation, either with the reduced task in MapReduce or in Monte Carlo, typically by taking all the random number simulation results and condensing them into one final result. This is a typical pattern too. You can find, for example, in the Boring project, which is distributed computing of Monte Carlo problems, a lot of different application scenarios. And this has its own characteristics and its own advantages and disadvantages when you talk about particular execution platforms. The next dwarf example is Backtrack or Branch and Bound. And this is a class of parallel computing problems where you have a large search space. This is typically structured, so you have some kind of data dependencies between the items in your search space. And now you want to go through this space and find some kind of result. For example, it could be a searching problem in a tree or something like this. And the question is now, how do you deal with that problem? What are good parallelization strategies? Divide and conquer is one kind of answer here. And branch and bound problems are also very common in scientific computing, for example, for combinatorial optimizations or for traveling salesman-alike problems. You basically want to achieve a parallelization of the checking of some sub-regions in the search space. And this can be done in different smart ways, especially with respect to a particular execution environment. If you want to take an example, one example is the well-known n-queens problem. So the n-queens problem is a hypothetical problem that can be mapped to real-world problems, where you take a chessboard and you take a number of queens, this is n, and you want to place these queens on the chessboard so that no two queens can attack each other. And when you do a brute force approach, this could look like this, as you can see on the slide now. So you place your queen and then you try all the different variations that result from this particular first queen placement, and you figure out if they are feasible or not. So brute force basically means you go through the complete search space and you look into each and every single possible solution in there. This is not very efficient, so one little bit more smarter approach would be certain branch and bound algorithm, as you can see here, where you immediately try to figure out from a given configuration what are feasible next steps, and you only try out these feasible next steps and you ignore all the other solutions that are obviously not working in this situation. So dealing with branch and bound, again, gives you a different scenario in your communication graph, in your task grouping, and you now need to figure out if this matches the environment or not. So in sum, Berkeley Dwarfs is a nice tool in order to find common terminology. So as with ordinary design patterns, one of the basic advantages is that if you talk in dwarf terminology, people start to understand each other more easily. The second thing is that you may find existing solutions, mathematical libraries, example algorithms, documentations, tutorials, books with respect to a particular dwarf. So this is a good guide to bring you into the right direction. So it makes a lot of sense to take your parallelization problem and first try to figure out, is this one of these dwarfs? And if this is the fact, can I make use out of the fact that I know, have an idea of the computational problem class? If you want to see real code, if you want to get deeper into that, there are two interesting projects on the web. The Open Dwarfs project, which gives you optimized dwarf implementations for particular target platforms like OpenCL or OpenAP, and also the Parallel Dwarfs project, which gives you some code examples for Visual Studio-based development environments.